Hello there guys. In today's video we're going to be learning about particular stuff from the periodic table, such as elements, atoms, ions, and orbitals, and isotopes too. First let's recall. We know that all matter is composed of building blocks known as atoms, but what does an atom look like? Let's quickly draw a circle here. This is going to be most of the volume of our atom, and let's use yellow to denote the nucleus. In our nucleus, we can find smaller particles such as protons and neutrons. Now we can draw some filling around the nucleus, and this is going to be our electron cloud, which composes of most of the atom's density, and this is also where an atom's electrons can be found. And this whole thing is the atom. So, most of the mass of an atom is found in the nucleus, while most of the volume is found in the electron cloud. Let's get to know the particles found in an atom. So we can call these the subatomic particles. And commonly, we have three particles in particular. So the first one is the positively charged particle known as the proton, which we can denote as P+. Next, we have the neutron, which is uncharged. It can be denoted as N raised to 0. And lastly, the electron, which is negatively charged, and we can denote this as E-. So, in every element, we have three main parts. X, which is the atomic symbol. In every element in the periodic table, rather. When we look at the periodic table, we can see there's things like AU, FE, H, O, Br, that stuff. These are the atomic symbols of each element. And the main parts of those are, like I said, X is the atomic symbol, and Z here, this is our atomic number. The atomic number is basically also the same as the number of protons. And we can denote the next one as A. This is our mass number, which can also translate into the number of protons plus the number of neutrons found in an element. But there's also one part that we don't normally include in atoms unless the atom is charged, and that's, like a guess, the charge. It can be plus or minus, depending if it's a cation or an anion. Now let's find out what those two mean. So, a cation. An easy way to remember this is, let's highlight the word cat. So, we know that cats have paws, and paws is something we pronounce when saying the word positive. So basically, you're saying positive. That's just a quick way to remember it. So let's reiterate that. A cation is a positively charged atom and has less electrons than protons. An anion is a negatively charged atom and has more electrons than protons. Now, how do you know if something has more electrons or less electrons than protons? Let's go back to our atomic number. In an element, the number of protons should always be equal to the number of electrons, unless it's a charged atom, which in this case, if we remove an electron, it becomes a cation, meaning it gets a plus charge. If we add electrons rather, we get a negative charge, making it an anion. Let's move on to the more mysterious guy, the neutrons. So, the number of neutrons in an element can be different, and isotopes are what determines that. So what are isotopes? It's basically the same element, rather two atoms of the same element, containing a different number of neutrons. And like I said earlier, the mass number is the number of protons plus the number of neutrons. The atomic weight of an element is basically the weighted average of each known mass of all of the isotopes of an element. So let's say you could have 15.98 AMU. AMU is atomic mass units, and this is what we normally use as the unit to determine the atomic mass of an element. Okay, so let's say we have 15.98, 16.02. Let's say these are all isotopes of oxygen. 15.96 plus 16.04. So let's say we add these all up and divide it by 4. Imagine you get 16.00 AMU. That's usually the mass we use to show the mass number of, rather the atomic weight of oxygen. You might run into it like 16.00 grams per mole. And that's it. Again, each isotope is just the same element of two or more atoms with different neutrons, a different number of neutrons. Now let's figure out how to read the periodic table. We know that there's rows and columns for the periodic table. And what are they called? So for rows, or rather the horizontal elements, these are known as periods, while our vertical friends are known as groups. So in each row or each period, elements should always, not always, but more or less, all of the elements of the same period are similar in size. But in a later video, we can find out more about the trends found in the periodic table. Now, for the groups, elements found in the same column should have similar electronic and chemical properties. What this means will be discussed in a later video. And let's move on to the orbitals. What is an orbital? So an orbital is a region in space that is high in electron density. Let's visualize that. So basically, let's say this is your entire atom. Each ring surrounding it is a sub-energy level of an orbital. So this is your first orbital. This is your second orbital. And each time you make an orbital around the next orbital, that orbital is going to have a higher energy output than the last one. Because the further you are from the nucleus, the more unstable you get. And we know that the higher the energy, the more unstable. But let's move on and find out more about orbitals. There are 4 different kinds of orbitals, and this is how you can easily identify them. So let's say this is the whole periodic table. So this is basically just the way you have to look at it. This is our S block, this is our P block, this is our D block, and this is our F block. But what we're going to be talking about today is the S and the P blocks. And in the first shell, found here, there's only one orbital, an S orbital. So let's say we're talking about beryllium. The electron configuration of beryllium would be 1s2, 2s2. Now, how do we convert this into an orbital diagram? You can basically write it like this: 1s, 2s. We write these in order of increasing energy. Now, since there's 2 electrons in the first orbital, we write it like that. There's also 2 electrons in the second orbital, so we're going to write it like this. But what does it look like if we have a p orbital? Let's say we have carbon. Carbon is 1s2, 2s2, 2p2. Now we're going to write it like this: 1s, 2s, 2p. So this time it's going to work differently. Let's write the 2 electrons here, 2 electrons here. But we have a rule in quantum mechanics known as Hund's rule. So normally you'd expect that you would have to draw it like this: 1 electron here, another electron there. That would be incorrect. The reason that's the case is because the Hund's rule states that each orbital should be filled up with an electron first before being paired up with another. And let's just keep it like that. So basically, what that means is we would have to write it like this: 1, 2. Not 1 and then 2. Not like that. That's wrong. Let's move on to the S and the P orbitals and find out what else they mean. So for our S orbital, it's more stable and has less energy than a p orbital. So what this looks like is basically this. More or less, it kind of looks like the atom we drew earlier. But yeah. So the thing in the center is still our nucleus. And it's lower in energy because the electrons are kept closer. To the nucleus. Now, for our p orbital, it gets a bit more complex. Usually, this is what it would look like. So it has a dumbbell shape. And these dumbbells are where we can find our electrons. And in the center, there is no electron density. This is still going to be our nucleus though. But regions where there's no electron density are known as nodes. And that's all you got to know about that word. So it's basically just an empty space in between the 2 sides of the dumbbell. And the reason that this is higher in energy is because these 2 sides are basically repulsing each other, meaning that both electron densities are kept further away from the nucleus, making it a bit more unstable than the s orbital, meaning it has a higher energy output. And let's reiterate the orbitals again from earlier. So for the first orbital, or rather the s orbital, the s orbital can only hold 2 electrons. Basically s2 and then p6. Why? Let's draw it again. So let's say we have a 2s orbital here. We can only hold a maximum of 2 electrons. For a p orbital, we can hold a maximum of 6 electrons. The last thing we need to know is what's on the outermost orbital of an atom. Let's say this is our atom, this is the first orbital, and this is the second orbital. Now, in this outermost orbital, we can find things known as valence electrons. These valence electrons are the electrons that mainly participate in bonding. Why? Because the hold that the nucleus has on them is weaker than the hold of the ones on the first orbital, meaning that they are more loosely held and are more willing to perform bonding, to undergo bonding. So how do we know how much valence electrons an element has? So let's say we have the first row of the p block here. So that's boron, carbon, nitrogen, oxygen, fluorine, and neon. Let's also include lithium and beryllium. So lithium, being in the first group, has 1 valence electron. Beryllium, being in the second group, has 2 valence electrons. Boron, being in the third group, has 3. And that's basically the pattern. Noble gases have 8. Always remember that, because the noble gases are already stable and usually they're not willing to undergo bonding. So this is basically what it looks like in a Lewis dot notation. So let's say we have our fluorine. So it would look something like this. There's always going to be 1 electron ready to perform bonding. But that's it. That's basically what valence electrons are. And if you're wondering, let's go to the second period of the p block. So that's aluminum, silicon, phosphorus, sulfur, chlorine, and argon. We follow the same pattern as earlier, so we just follow these 6. Aluminum would have 3, silicon would have 4 valence electrons, phosphorus would have 5, sulfur 6, chlorine 7, and argon 8. And that's it. Now let's apply this to one problem. So, this problem reads, while the most common isotope of nitrogen has a mass number of 14, a radioactive isotope of nitrogen has a mass number of 13. Nitrogen 13 is used in PET, or positron emission tomography, scans by physicians to monitor brain activity and diagnose dementia. For each isotope, give the following information: the number of protons, the number of neutrons, the number of electrons in the neutral atom, the group number, and the number of valence electrons. So let's go through this step by step. Our first question is the number of protons. So we have nitrogen 14 and N13. So what these numbers mean is the mass number that the atom has, rather the element has. So this is nitrogen with a mass number of 14, and this is nitrogen with a mass number of 13. Now how can we denote, or rather how can we find out the number of protons it has? Basically, we can just refer to a periodic table. So nitrogen would be what element on the periodic table? Or rather, what's its atomic number? So we have hydrogen, we have helium, we have lithium, we have beryllium, boron, carbon, nitrogen. So, hydrogen is 1, helium is 2, lithium is 3, beryllium is 4, boron is 5, carbon is 6, and nitrogen is 7. That means the atomic number of nitrogen is 7. And we know that the atomic number is basically the same as the number of protons, meaning our answers for both should be 7 protons. Moving on to the next question, we have the number of neutrons. How can we find this out? We know that the mass number, or our A, is equal to the number of protons plus neutrons. So basically, we already have the number of protons here, and we can just do some basic math and subtract the number. So for N14, we have 14 minus 7, and we have 7 neutrons. That's for N14. For our N13, we have 13 minus 7, which is 6. So we have 6 neutrons for N13. Moving on, we have the number of electrons in the neutral atom. But since there are no ions present, and we know that N14 and N13 are both neutral atoms, we just find the number of protons for both. I mean the number of electrons, sorry. Now how do we find this out? As I stated earlier, the number of electrons should be equal to the number of protons in a neutral atom. And we know that both of them are neutral since there's no charge and they're not ions. So basically, we just refer to our answers from the first letter, and that's 7, meaning both of them have 7 electrons. And that's how you get the number of electrons. If it were to be charged though, let's say you have N2 minus. When you see a negative number on the charge, assume that's the number of electrons you have to add, because adding electrons adds a negative charge. So basically, if this were to have 7 electrons in its neutral state, adding 2 more would turn it into 9 electrons. And if we were to have N2 plus here, that's us taking away 2 electrons. So minus 2, that would be 5 electrons. And lastly, wait, no, there's 2 more numbers. Sorry, my bad. So for our fourth question, the group number. Again, let's reiterate what we have on the second period of the periodic table. We have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Our lithium is in group 1A. Let's write in blue, sorry. Our beryllium is in 2A, boron would be in 3A, carbon in 4A, nitrogen in 5A, oxygen in 6A, fluorine in 7A, and neon in group 8A. So, this means that our group number should be 5A for both N13 and N14. Because the only way for the group number to change would be changing the number of protons, but that would change the identity of the atom. Because the identity of an atom is dependent on the number of protons. If it has 7 protons, that's a nitrogen atom. If it has 8 protons, it's going to be an oxygen atom. And if it has 9, that's going to be a fluorine atom. And let's move on to the final question. The number of valence electrons. So how do we determine the number of valence electrons? The number of valence electrons is basically equivalent to the group number. So If lithium is in 1A, we would have 1 valence electron. Beryllium is in group 2A, we would have 2 valence electrons. If boron is in group 3A, we would have 3 valence electrons. Carbon at 4A means that it has 4 valence electrons. So for our nitrogens, both N14 and N13, we would have 5 electrons. Rather, 5 valence electrons, ready to undergo bonding. This is how you would draw that in a Lewis dot structure. And nitrogen commonly forms 3 bonds in organic structures. And that's basically all for today. That's all you guys need to know for the first lecture. Thank you very much for watching, and I hope to see you again on the next video.